let's continue our discussion. So now we're going to look at another example. Here we need to find V naught of t, which is the output voltage across this element for t greater than 0. And we can analyze the circuit that it has one voltage source, one current source, and one voltage dependent voltage source. And for t less than 0, the switch over here is open, and for t is equal to 0, at t is equal to 0, the switch will then be closed. So once the switch is closed, we can see that this current will kept flowing in this loop, because this would be the path with the least resistance. So keeping in mind all these points, including that this voltage dependent voltage source depend upon the voltage across this element. So we need to analyze the circuit before we start attempting it. So let me just clear it and let's see how we can solve it. So the first step is to write down the generic equation of the output. So we already know that for first order circuits, V naught t is k1 plus k2 e raised to power minus t by tau. And for the second step, first thing we need to do is we need to find the capacitor voltage at t0 plus. That is the initial condition. And for initial condition, we analyze the circuit at t0 minus, and we know that the voltage across capacitor is continuous. So if we analyze the circuit at t0 minus, that will be the same voltage at t0 plus. So if we redraw the circuit for t0 minus, we can see the switch is open. So here we can see the switch is open, and the capacitor will be at steady state because it would be fully charged. So it would be replaced by an open circuit. So here we can see this is now an open circuit. So the voltage we will get over here at this time will be V naught 0 minus. So this is V naught 0 minus, which is same as VC 0 minus. So now we need to find out this voltage. Okay, let me just clear it. So here we can see voltage across this resistor is 12 volts. How we can see that? Because we can see that since this is an open circuit, there is no current going in this direction. So all this current will go through this branch, and it will flow through this branch, and it will return back to this source. So the current that is flowing in this branch is also 3 ampere. So 3 into 4, it is 12 volts. So the voltage across these two terminals is 12 volts. And now if we want to find the VC0 minus, here we can see that since VA is 12, so this voltage source will be 24 volts. Let me just clear it. So, and we know the polarities here, this is minus and this is plus, and VA is 12. So you put VA over here, it is minus 12. So now we are interested in finding out the voltage across these two terminals. So what we can do is we can apply KVL in this loop, as we have done in previous examples. So in this case, if you apply KVL here, this would be the KVL equation. So if you simply apply the KVL loop, you will end up with this expression, and we can see it for ourselves as well. So if we start from this point, let's say it is minus 12, then minus 24, then it is minus 24, then plus VC0 minus is equal to 0. So this is the KVL loop that we have written down. And if we keep this on this side and take these values on the other side, we will end up with this expression. So you can try it yourself. So in this case, VC0 minus is 60 volt, and we know that which is same as VC0 plus. So we have got the initial condition, and we know its value is equal to K1. K1 plus K2. We have already seen it in the previous examples. So now we need to find V naught 0 plus. So here we can see V naught 0 plus and VC 0 plus are both the same. So output voltage is also 60 volts. And now we are going to find the steady state value, which is V naught at t is equal to infinity. So it means at t is equal to infinity, what will happen? The switch will be closed. Secondly, the capacitor will be fully charged and it will be replaced by an open circuit, and then the voltage at the output will be V naught infinity. So if you look at this circuit, here we can see the switch is closed, the capacitor is fully charged, it is replaced by an open circuit, and we are interested in finding out the voltage at the output over here. So since this is now short circuit, we see all this current will flow through this least path of least resistance, and no current will be flowing in this direction. So if no current is flowing here, no current is flowing in this direction, because this path is also open, so no current will flow in this direction. So if there is no current flowing in this branch, VA will be equal to 0. So if VA is equal to 0, So we can see this voltage source will be equal to 0, and if a voltage source is equal to 0, it means it is replaced by a short circuit. So if you look at the output, the only voltage source we see is this voltage source, and we can see this positive terminal is appearing here, and this negative terminal through this branch is also appearing over here. So V naught infinity is nothing else but the same voltage source that this is, which is 24 volts. So we can see it over here as well. Let me just clear it. So this VA is 0. So output at infinity or the steady state value is 24 volts. Okay, so now we need to determine the time constant, and for that we have drawn the original circuit. And first thing we need to do is we need to find the time constant in case of this circuit. And since we have a capacitor, so the tau value will be determined by R Thevenin C. And for finding out R Thevenin, we can see since we have a voltage dependent voltage source, we cannot find the R Thevenin from the conventional method. We have to find the open circuit voltage and the and the short circuit current to find out R Thevenin. So this is how we are going to find R Thevenin, which is VOC over I short circuit. So what we are going to do is, in order to find the V open circuit means at that time the switch will be closed, and V naught infinity will be actually the V open circuit in our case, so which is same as 24 volts. We have already seen it. So for I short circuit, what we do is we short these two terminals, and we are going to see how much current is flowing in this direction. So for short circuit current, this is the current that we are interested in. So again, we can see this 3 ampere current will be just flowing in this branch, and we have these two sources. And since we know that there is no current flowing in, now current will be flowing in this direction because this is no longer an open circuit. So we need to find the current that is flowing through I short circuit. So for that, first of all, we can see that since this is short circuit, we can determine the equivalent resistance in this branch. So you can see these two resistors are now parallel. So it is 2 ohms. So 2 ohm resistance is on this side. And if we apply KVL in this loop, we can write down the equation like this. So if let's assume the current is flowing in this direction like this. So in this case, let's see. So it would be I short circuit current will be flowing through this equivalent resistance branch. So this will be plus, this will be minus. So it is 2 ohms into I short circuit. Then you have minus 24, and then you have minus 2 VA is equal to 0. So this is the KVL equation that you get in this loop. So in this case, if you look at VA is nothing else but the current is going from bottom to top. So polarity is positive, negative. So VA is minus 2 I short circuit. So you plug this value over here. From here you get I short circuit, which is 4 ampere. So I short circuit is 4 ampere. V open circuit is 24 volts. R Thevenin comes out to be 6 ohms. So with this gives us the tau value of 12 seconds. So we need to determine the constants K1 and K2. So we know that the steady state value is K1, which is 24, and the initial condition is 60, which is K1 plus K2. So you put K1 is equal to 24 over here, you will get the value of K2. K2 comes out to be 36 volts. And if you plug all these values in the result, which is V naught is equal to K1 plus K2 e raised to power minus T by tau, you will get this answer. This is the required answer in our example. So in this case, we can see that whenever you have a dependent source in your circuit, make sure that you find R Thevenin using this method, which we have already seen in the case of Thevenin and Norton. Okay, let's look at an inductor example. Here we need to find V naught T for T greater than 0. And here we can see we have an inductor in this circuit, and for T less than 0 the switch is closed, and for T greater than 0 the switch will then be open, and we need to find the voltage across this resistor. So first of all, write down the form of solution that we require. So in this case, output will be K1 plus K2 e raised to power minus T by tau, and we need to find the initial inductor current, which is I0 plus, and for that we need to find I0 minus. So for I0 minus, inductor will be in steady state. It will be replaced by a short circuit. Switch will be closed, and we need to find how much current is flowing through this inductor at I0 minus, which is this. So this is how the circuit would look like, and we need to find out the initial inductor current. So here we can see the voltage source, the current leaving the voltage source is now divided between these two branches like this. So we can find the value using voltage division or voltage division in simple terms. So we keep in order to find this current, we first we can see that the voltage across these two terminals is the same. It is 6 volts, which is across this branch and this branch. So in this case, we can see since the voltage across this resistor is 6 volts, the current will be 6 divided by 2, which is 3 ampere. So by looking at the terminals which are connected across both branches, we can see the current flowing in this branch would be 3 amperes, and I0 plus would be the same current, that is 3 ampere. So in this case, what we need to do is what we are going to do is we are going to replace the inductor with the current source, and then analyze the circuit for T0 plus. So for T0 plus, inductor will be replaced by a current source. Current direction will be downward as the current direction of IL0 plus, and the switch will be open like this. So here we need to find V naught 0 plus. So here we can see since the switch is open, this source is dummy. अब ये जो करंट यहाँ से निकल रहा है, this all of this current will flow through this branch. So since this polarity is plus minus, but the current is flowing from bottom to up, so V naught 0 plus will be a negative value. So 3 into 2 will be 6 volts. So V naught 0 plus is minus 6 volts. So here we can see it is minus 6 volts. So we have found the initial value of the output voltage V naught 0 plus. So now we need to find V naught at infinity, which is the steady state value after switching. So after switching, switch will be open and inductor will be short circuit, and we are going to find what is V naught T. So in this case, the circuit would look like this. So here we have replaced the inductor with a short circuit. Switch is open, so this source is a dummy source, and at infinity, all the energy stored by the inductor will be dissipated across the resistors. So at infinity, output voltage will be equal to 0 because there is no source connected. So V naught infinity is 0. So now we need to find the time constant. So for time constant after switching will be done in a way that we are going to analyze the circuit and see if there are any independent sources. Since there are no dependent sources, we don't have to worry because we can just find out the value of R Thevenin by analyzing the circuit by putting all the sources equal to 0, and through the terminal of the capacitor or inductor we are going to find R Thevenin. So here we can see if this source is not included in this case. If we look from the inductor side, all these resistors are in series. So simply what we do is using this relationship for the case of inductors, where tau is equal to L by R Thevenin, we can find R Thevenin as by looking at the circuit. This source is 0, and by looking through the inductor port, we can see 2, 4, and 2 are all in series. So it is 8 ohms. So we've got all the required values. So tau comes out to be 0.25 seconds, and the solution would be of this form because the initial condition is K1 plus K2, which is minus 6. K1 is equal to 0, so K2 is equal to minus 6. So output voltage will be K2 times e raised to minus t by tau, and this is the required solution. So this is how we solve the first order circuits and find out the required output voltage. So let's conclude this session here. In the next class, we're going to talk about what happens to a circuit when we give it a step response. So let's conclude the session here. Thank you very much.